Welcome to the flock. Let's dive into some questions like how many grams are needed to make 500 milliliters of a 0.879 molar solution of silver nitrate, along with some M1V1 equals M2V2 practice, such as these problems. Stick around to see how they're solved. In this first question, they're asking how many grams are needed to make 500 milliliters of a very specifically concentrated solution, 0.879 molar solution of silver nitrate, AgNO3. Whenever we are asked for grams and we are given a volume, we're going to use the following setup for dimensional analysis, or stoichiometry. So let's go ahead and do that. We'll draw our magical line to freedom, as I like to call it, and put our goal of grams of AgNO3 at the end of our line. We have 500 milliliters that we are trying to make of silver nitrate solution, and we know that we're going to need to convert out those milliliters in order to use the molarity and cancel liters in the end, since we know that there are 1,000 milliliters in 1 liter. The next thing we're going to use is our molarity, 0.879 M. Now that big M is not standing for McDonald's. It actually means 0.879 mole over 1 liter. I like to write it like that when I see a big M, just so I don't forget that it is a conversion factor to plug in next. So that's what I'm going to do now, and the next thing on my line. I'm going to plug that in so I can cancel out my liters. 0.879 moles in 1 liter of the silver nitrate solution is what we're trying to create. Now, in order to get to grams, which was the goal to begin with, I need the molar mass of silver nitrate. In order to do that, I add up the pieces from my periodic table. Ag is roughly 107.8 grams, nitrogen is roughly 14.007 grams, and oxygen is roughly 16 for each atom, and there's 3 of those. If you add those 3 pieces together, you get 169.807 grams per 1 mole of silver nitrate. Now all I have to do is multiply the values across the top and the values across the bottom, then divide the 2 for my final answer, which happens to be 74.63 grams of silver nitrate. Now, since this question actually pertains to what you'll probably see in an experiment or in a lab setting, let's quickly go through how you would actually do this. You would take your 74.63 grams of silver nitrate, a solid, and weigh that out on a scale. You would then need to take your 500 milliliter volumetric flask. Now don't judge my drawing here, I am not professing to be an artist. And then you would add your 74.63 grams of silver nitrate directly to the flask, or you would make a slurry out of it first and add it to the flask. You would then fill the rest of the flask up with water until you get to the 500 milliliter mark. That would give you your 0.879 moles per liter solution in your 500 milliliter volumetric flask. Let's move on to our dilution equation, M1V1 equals M2V2. Here we'll be calculating for M1. If hydrochloric acid comes in a big jug of some question mark concentration solution, that's what we're solving for, and often we only need 0.1 molar solution to carry out experiments, and we were going to make 500 milliliters of that 0.1 molar solution using only 4 milliliters of the stock, then what is the concentration in my big jug, my original jug of hydrochloric acid? Before we can plug and chug, it's important to label each one of these for what they are. What we're solving for is M1. Our M2, our goal concentration, is the 0.1 molar. Our initial volume, what we use initially to make the solution, is the 4 milliliters of the stock. That's our V1. And our V2 is 500 milliliters. That's what we have in the end. Now that we know all the pieces, we can simply plug into our equation of M1V1 equals M2V2. M1 here is like our X value, what we're solving for. And that's multiplied by our value of V1. Now this is in milliliters, and this equation calls to use volumes in liters. So we have to move back the decimal 3 times to convert milli to liter. In this case, that would then be 0.004 liters of the stock is used in our V1. We're going to set that equal to M2, that's our 0.1 molar, the goal concentration, and that's multiplied by not the milliliters again, we need to convert it to liters first before we can plug it into this equation. We'll move back our decimal 3 places to get rid of the milli part of it, and end up with 0.5 liters that we plug into our equation. Let's multiply the two numbers we have together first. For 0.05, and we set that equal to 0.004 times x. Now, just like in any math problem, we need to isolate the x by itself, so we're going to divide off the 0.004 from both sides. Now we can see that our x is equal to 12.5 molar. We know that our initial big jug of hydrochloric acid had a concentration of 12.5 moles per liter. Whew, that's pretty concentrated. By the way, at room temperature, that stuff is fuming, literally fuming. Now that you've had a bit of a refresher of M1V1 equals M2V2, see if you can figure this one out yourself before we go through it together. Go ahead and pause the video here to give the calculation for V1 a try on your own. By the way, these are real values. In Red Bull, the caffeine content is 80 milligrams per 237 milliliters. So first we want to figure out what's the molarity of the caffeine in a Red Bull solution. And I gave you the molar mass here, 194.19 grams per mole for caffeine. We know that molarity is moles per liter, so we need the grams, the milligrams, to be converted to grams and then to be converted to moles. And we know that we need liters, so the milliliters will need to get converted to liters. Let's start with the caffeine. If we have 80 milligrams to start with, we know that there are 10 to the negative 3 in every milli, and that'll get rid of this milli value here, and I'll be left with grams. Now I need to convert to moles. I'm going to use the molar mass that I was given, 194.19 grams in 1 mole of caffeine, in order to cancel out the gram aspect and be left with moles. So now I know that the moles of caffeine are 80 times 10 to the negative 3 divided by 194.19, which is a value of 4.12 times 10 to the negative 4 moles of caffeine in Red Bull. That'll be my numerator for molarity. Now I just need to convert my milliliters to liters. I'm just going to move my decimal over 3 spaces to 0.237 instead of 237. If I take that and divide my mole value by 0.237 liters, that should give me my molarity. I end up with a value of 0.0017 moles per liter, or big M for molarity. So now let's move on to part 2. If the manufacturer starts out with a very concentrated solution of caffeine, 0.15 molar, how much of that concentrated solution do we need in order to make just 1 can of Red Bull? Let's first identify what each value represents in our dilution equation. 0.15 molar would be the M1. We already found out that in Red Bull, the caffeine content is this concentration. That would be our M2. Our final total amount in a can is 237 milliliters, or 0.237 liters, as we found out before. And that would happen to be our V2, the total volume of a can. So then what we are solving for is our V1, our initial amount of stock concentration. How much did we use of that per can? So M1 is 0.15. We're going to multiply that by X, our V1. You could also just write V1 here if you're more comfortable with that. Either way is fine. Set that equal to our M2, our 0.0017 that we calculated before, times 0.237 liters. Notice I kept it in the liters because to plug it into the equation, you need to have it in liters, not milliliters. When we multiply these two values together, we get 4.12 times 10 to the negative 4, and we set that equal to 0.15x. Divide off the 0.15 from both sides. And that gives us a final answer of 0.0027 liters for our V1. Or in other words, that gives us 2.7 milliliters of caffeine is added to every single can of Red Bull. Hopefully you're getting the flow now. Go ahead and pause the video here to see if you can solve for M2 on your own. In this question, if I had 25 milliliters of very concentrated nitric acid solution at 18 molar, and I haphazardly just added 675 milliliters of water to it just to try and dilute it, what is the new molarity of the diluted sample? So my V1 here would be the 25 milliliters, that's the initial volume I'm starting with. My V2 is 675 milliliters, the total that I end up with. And I know that my initial molarity is 18 molar, so my M1. Again, I'm solving for M2, just as I kind of insinuated before. So let's plug and chug into our equation. We'll have 18 for M1 times our V1, 25. I hope you didn't use 25 because that's in milliliters and we need it to be in liters. So that would be 0.025 liters set equal to M2 or X times 0.675 liters. Again, because we don't want milliliters, we want it in liters. When we multiply these two values together, we get 0.45, and we set that equal to 0.675x. In order to get x alone, we need to divide off the 0.675 from both sides. And we have a final answer of 0.666 repeating, so 6667, and that would be in units of moles per liter, equivalent to our X, which was our M2. In other words, after this very large and haphazard dilution, I would go from having an 18 molar stock solution to less than a molar of diluted solution. All right, here's your last one, calculating for V2. Go ahead and pause the video here and see if you can give it a try. If you've seen my previous Zootopia video, you know that I am not known for my pronunciation of words correctly, necessarily. So forgive me if I say this word incorrectly. If you were given 50 milliliters of a 9.2 times 10 to the negative 2 molar stock solution of myristicin, again, I have no idea if I said that correctly or not, which is actually a compound found in nutmeg, something that you would keep in your spice cabinet at home and add to many fall delicious recipes, but it has a chemical in it that's literally similar to MMDA, an amphetamine. It's also responsible for hallucinogenic effects, and the concentration that's given here, the 9.2 times 10 to the negative 2 molar solution, would be a toxic concentration. In other words, nutmeg could literally be lethal. And another reason why, if you're pregnant or considering becoming pregnant, you should avoid large amounts of nutmeg. So let's say you wanted to dilute this very toxic concentrated solution to 2.7 times 10 to the negative 4 molar instead. How much water would we need to add to it in order to do so? Let's identify what's what. Our initial volume is 50 milliliters. That's our V1. Our initial concentration is the really toxic one at M1. We want a new molarity of 2.7 times 10 to the negative 4. That's our M2. And we are, hey, calculating for V2. Just kind of like the title states. So let's take our M1, 9.2, and I'm just going to put an E there because that's how I'm going to plug it into my calculator instead of that whole 10 to the negative 2 caret thing. E negative 2. Multiply by our V1. Again, make sure it's in liters, so move the decimal over 3 spaces for 0.05 instead. Set that equal to our M2, the 2.7, E negative 4, because that's how I'm going to plug it into my calculator, times X for our V2. When I plug these two values into my calculator and multiply them together, I get 0.0046. I do highly encourage you to use that second EE button in order to do that instead of the whole 10 caret negative 2, all that jazz. It just doesn't work out very well in the long run. We're going to set that equal to 2.7 E negative 4 times X. In order to get X alone, we need to divide off that very small value from both sides. So 2.7 E negative 4 gets rid of it from the X side. 2.7 E negative 4, divide that side. When we do so, we see that X is equivalent to 17.037 liters. Now remember, this is V2, and V2 is a total volume. That means that this also includes the initial milliliters we started with. So in order to figure out how much water we need to add to the already starting amount of 50 milliliters, we need to first subtract the two from each other. So 17.037 liters minus 0.05 liters, that was our 50 milliliters that we started with, would be how much water we need to add to this 50 milliliters to make it not so toxic. So our final answer should be 16.98 liters is how much water we would need to add to this to dilute the toxic myristicin. In this lesson, we touched base on using stoichiometry and molarity in order to figure out the amount of grams we'd need to make a specific concentration of a solution, and also how to solve for each variable in the dilution formula M1V1 equals M2V2. Please give this video a giant quacks up and subscribe to Duckonta for some more ducky content. Hope to see you again soon.
No ducks, no glory.